Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So our next talk is a paper by Vasilis Tsikanis, Alec Agarwal, Haipeng Luo, and Robert Shapire on fast convergence of regularized learning in games. And Haipeng Luo will give the talk.
So congratulations.
Hi, I'm Haipeng from Princeton. So this is joint work with Vasilis Tsikanis, Alec Agarwal, and Rob Shapire, all from MSR New York. And actually, the primary author of this work is Vasilis, and this is also his slides, but unfortunately, he has some sort of visa issue and cannot make it this time. So here I am to tell you about fast convergence of regularized learning in games. So in modern computer systems, there are many actual game theoretic scenarios. For example, in internet routing, a set of nodes want to pick a path to send some traffic, and they all want as small latencies as possible, which can be seen as a game between these nodes. And another more standard example is advertising auctions, where a set of bidders try to bid on a specific search or a web page to display their advertisements, which can again be seen as a game between these bidders. So games are really everywhere in our life. The question is, how do the players behave in the game? So classical game theory says that players play according to Nash equilibrium, so that none of the players want to deviate from the current action. The problem about Nash equilibrium is that it's computationally hard to find, and it's not clear how the players arrive at the equilibrium. However, in real life, instead of playing a one-shot game, the more often scenarios is that the players are allowed to play the game repeatedly and using some sort of adaptive strategy. So they can learn to play well over time from past experience. For example, there are some dynamic bid optimization tools in online act auctions where they try to learn to play a bit well for you over time. So now the question boils down to what kind of adaptive strategies should the players use? Well, it turns out that we can borrow something from the online learning literature, something called no-regret learning. So roughly speaking, no-regret learning means that on the average, each player is doing almost as well as any best fixed strategy. And there are many simple algorithms to achieve no regret, such as multiplicative weight update, regret matching, follow the regularized leader, and mirror descent, etc. And the good things of using no-regret learning in games is that, first, we can show that the empirical distribution of the players converge to something called the coarse correlated equilibrium, which is a generalization of Nash equilibrium. And moreover, the social welfare, which is the sum of the player utilities or the overall performance of the game, actually converges to some approximate optimality under some mild condition of the game. So these are known convergence results. And the convergence rate is governed by basically the magnitude of the regret, and is typically of order 1 over square of t. And in fact, this 1 over of square of t rate is impossible to improve in the worst case. And so you might think that this 1 over square of t is also inevitable in playing games. However, if you think about it, when playing a game, you are not exactly in a worst case scenario. You are in a very specific game dynamic where each player has their own objective to achieve. So this leads to the main question that our work tries to answer. Can we converge faster than the adversarial 1 over square root of t rate when all the players involve some kind of no-regret learning algorithms? And the answer we give in this work is yes. The high-level main result is that we prove that if each player's algorithm satisfies the following two properties. First, they have to make some sort of stable predictions. And second, the regret is controlled by the stability of the environment. Then we can converge much faster than the 1 over square of t rate. Moreover, these conditions are not stringent at all. They are very natural and can be respectively achieved by regularization and recency bias. So regularization is familiar to this community, and recency bias means that you put more weights to the recent outcomes. So this is the high-level main results. Now let me get into more details. So again, we consider some sort of repeated game model where there are n players in the game, and each of them has a strategy space Si, and some utility function that maps from a profile of all the players' action to a utility, let's say between 0 and 1. So another way to think about it is that Si is simply the set of all available actions that player I can pick from. And the utility is just your reward function. And for example, in the auction case, all the possible bids is your action space, and the utility is the value of the item minus the price that you pay to win it. And in the routing case, all the paths in the network is your action space, and the latencies, or rather the negative latencies of the social path is your reward. So now the game is going to be played for T rounds. On each round, each player has to decide a distribution over its own action space. So let's say the distribution is PTI, and then you draw a single action from it and play it. So after that, each of the players receives the expected utility in terms of their own utility function. And in addition to this, you also get to observe some utility vector, UTI, where each coordinate SI is the expected utility had strategy SI been played. In other words, so we assume player I played action SI, and we take the expectation with respect to the randomness of all other players. So this is going to be one coordinate of the utility vector. Okay, so this is the model, and if you are using no-regret learning algorithm, then PTI is going to be the output of the learning algorithm, and the utility vector is your feedback to this learning algorithm. So regret is roughly speaking, is the gain from switching to a best fixed strategy. So more formally, here, the second term is just your expected utility of the algorithm. And the first term is to switch your action for player I to a single fixed action SI all the time. And you see how much you can gain from this switching. And regret for player I is exactly measuring this improvement over all the possible action. And as I mentioned before, many algorithms achieve regret of square root t, and it's impossible to improve in the worst case scenario. So again, our main result is to give some general sufficient conditions that I will mention later, such that the following thing happen. First, instead of having a square of t regret, each player's regret is only t to the 1/4, if this condition is satisfied. So this also immediately implies that the convergence to the coarse correlated equilibrium is at the rate 1 over t to the 3/4, again faster than the previous 1 over square of t. And second, the sum of the player regrets is actually just a 1. So this is non-trivial because if you just sum over the player's regret using theorem 1, you still get t to the 1/4. And now we are saying that the sum of the regret is actually independent of t. It's just a 1. Meaning that we are considering some sort of global information, and some of the regrets get cancelled when we do this kind of sum. Okay, and as a corollary, this means that the social welfare of the game converges to some approximately optimum welfare at the rate 1 over t, if the game is smooth. So smoothness is defined by Rakhlin, and it's the main tool for proving welfare bounds, and it's very mild and applicable to many useful games. And we are saying that under this assumption, our convergence rate is 1 over t, faster than the previous 1 over square of t. So these fast rates are ensured as long as the conditions are satisfied. And now you might ask, what if any of the players is not behaving in this nice way? Well, to answer this question, we give a black box approach to modify any of these algorithms into a more robust version, so that if everyone is nice, then you still converge fast. Otherwise, you will have the worst case square of t regret against any adversarial sequence. So it's kind of the best in both worlds. So we are definitely not the first one to consider fast convergence in games. So these two are the most related work. And they all consider convergence to Nash equilibrium in a two-player zero-sum game at the fast rate 1/t. And our work attribute on the inside of the work by Rakhlin and Shridharan. However, the improvements are the following. First, we move from two-player zero-sum game to general multiplayer games. And second, we can consider convergence to the coarse correlated equilibrium and also the optimal welfare instead of just the Nash equilibrium. And third, instead of just studying some specific algorithm, we give a set of sufficient conditions to ensure fast convergence rate. And on top of it, we give some new example algorithm to satisfy these conditions. And for the rest of the talk, let me just focus on one specific result on the individual regret. And for the rest, please come to my poster. And so why can we expect faster rates? Well, think about it in this way. If your opponent doesn't change his distribution a lot, then intuitively it means that your expected utility for any action is also going to stay close between iterations, which means that the iteration of your last round is going to be a very good proxy for the next iteration. So just based on this intuition, it's very natural to propose the following two conditions. First, you want your algorithm to make stable predictions, which means PT and PT minus 1 should be close. And second, you want the regret to be controlled by the stability of the utility sequence, which is measured by the difference between UT and UT minus 1. So let's just forget about the other parameters here. But if we combine with the previous argument, your stability, your utility sequence is stable as long as your opponent is stable. And now if you choose some optimal parameter, you will get the rate t to the 1/4. And this is a simplified version of our conditions. Our actual condition in the paper is more general. But let me skip this and see whether there's an actual algorithm that can satisfy these conditions. So first, let's look at hedge, which is a classical no-regret learning algorithm. And it says that the weight for action Si should be proportional to e to some learning rate eta times the past cumulative performance of this action. And now we are going to add a little bit recency bias to this algorithm to arrive at this. So here, basically, you are just doing a double counting of the last utility. So in the exponent, the blue term is exactly counting the utility of the last round for an actual time. So, which means we are kind of optimistic and believe that the utility for last round is a good proxy for this round. And let's call this optimistic hedge. And it's actually not our algorithm. It's proposed by Rakhlin and Shridharan. But what we show is that this algorithm satisfies both of our sufficiency conditions. So the intuition is that because of the optimistic idea, if the utility sequence is stable, then our regress will be small. And for the stability, because hedge can be seen as some sort of for the regularized leader, and regularization implies stability, which is kind of well known. So this is the idea. So putting everything together, our conclusion is that optimistic hedge can ensure t to the 1/4 regret for each player. And we also generalize this optimistic idea to any for the regularized leader. And for the recency bias, instead of doing the double counting things, you can also do all kinds of different things. They are all in the papers. And this kind of algorithm, they all satisfy our conditions and will give you the fast convergence rate. So now let's look back at hedge and optimistic hedge. So you might think that the difference of these two algorithms are so small that the performance should also be close. Surprisingly, in our simulations, we see very different performance of these two algorithms. So our simulation is about a very simple auction game where there are 4 bidders bidding on 4 items. And here, this plot is about the maximal individual regret. So x is time, and y is the cumulative regret. And proof curve is for hedge. The red is for optimistic hedge. So as you can see, the regret for optimistic hedge is much smaller than hedge. In fact, it's even smaller than what our theory predicts. So our theory says that the individual regrets would be like t to the 1/4. But in the plot, we actually see something like 0.1. So it's an open question to see whether our upper bound can actually be improved to 0.1. Yeah. And so besides this, we also see a much stable performance of optimistic hedge. So in this plot, x is time and y is the expected bid. And you can see that after just a few rounds, optimistic hedge becomes kind of stable. And while hedge is still kind of oscillating. So to conclude, although the 2 algorithms are very close in terms of the formula, but they have very different performance. So just to conclude, the main take-home message here is that learning algorithm can enjoy a much faster rate in game theoretic environment. And we extend previous work to general multiplayer games and provide general sufficient conditions to ensure fast convergence rate. And the key components to satisfy these conditions are recency bias and regularization. And that's it. Thanks.
Thank you very much. If you have questions, please come up to the microphones.
Hi, very nice talk. I had a question about whether these results would extend to partial information settings, such as bandit settings.
No, we actually have thought about this question and for some time, and it seems like, so recently we find a paper which basically implies that you cannot get a better rate than 1/square of t in the partial information setting. So,
thank you.
Yeah.
Yeah, I just had a question. I didn't understand this part because you said, I believe, that at every time step you get to observe the expected utility of your action, as opposed to, it seems like you should just you should observe the utility, like a sample from the distribution over utilities?
Yes, that is also a good question. So again, if you just observe a sample of the utility, then you can show that it's impossible to do any better than 1/square of t. So it's kind of necessary to ensure fast convergence rate. If you want to get fast convergence rate, it's necessary to see the expected utility instead of just a sample.
So is there a reason that that's like a realistic assumption to make in some application?
I think so. I mean, it basically means that you can see your opponent's strategy. And yeah, I think it's kind of okay to make.
Thank you.
Can you comment on the robust version of your algorithm?
Yeah, actually I have backup slides for that. But so the idea is basically to do some sort of doubling check. And you keep track of the stability of your environment. And so when you have an upper estimate B on this stability, and whenever the actual stability exceeds this guess, you double it and restart your algorithm. So it's just a doubling check.
And you just pay a price in the log terms?
Yes.
Oh yeah, absolutely. Okay. Thanks.
Thanks.
Okay, thank you very much. Let's thank the speaker again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.